That's terrible. So like, I think signs is like x minus x cubed over two x squared plus x to the fifth over 5x squared, all of this keeps going. Every element. And then go back to the opposite, it's just one minus x squared over two x. Yeah.
Well, welcome back, folks. We are on the middle of midterm week, so we're getting through it. And we're just about done with chapter or section 9.5. So all the work in chapter 9 is going to culminate here, which means we're turning into the biggest part of the course, chapter 11, working with sequences and series. And a lot of people have mentioned it's an infamous chapter out of Calculus 2. This is pretty much the reason. Once we have everything on the table, and we're going to work through this in a really careful, very careful way. So let's just say it that way. Methodical, thank you. That word was deleted. Careful and methodical way. And this is going to be our target. We'll have this list of tests for series. The test for divergence is taking a limit. Test for geometric series. We'll look into P series, alternating series. And then usually this is the easy part of chapter 11, doing this work, and you're halfway through. Once you get beyond alternating series, that's when it kind of goes sideways, because now the comparison test or the limit comparison test, these three right here can pull in everything right above it. All of these can be used all at the same time, and absolute convergence is the literal worst. So when it comes to all of that, everything here is really interconnected in a really high way. But once we're actually getting into power series, Taylor series, Maclaurin series, we throw in these tests, the ratio test and the root test. This is one we're probably going to use the most, and they're really not too bad. They're just really taking the limit of a right kind of sequence. If it comes out a certain way, we'll say a series is convergent or divergent, or the test has failed. And so this is pretty much what it's all about. Notice though, the last thing on this document is the integral test. We already know how to do this test in a certain sense, because when you apply the integral test, convergence of a power series will happen if and only if the improper type 1 integral, this one specifically, converges. But that just takes us all the way back to section 7.8. It's the last one on these notes because it's the hardest test to use. And this is going to be a set of notes that is really provided on the real exam. So it's organized not in the way the tests come up. It's organized in the sense that if you throw a random problem, here's where you want to start looking, see if these tests apply. And if they don't, we start to using more and more powerful tests until we get to that one, the test of last resort. So that's the idea of what we're getting into. What it doesn't explain is why we get into that section. What's the purpose of all that stuff? You could say it's fun. You're looking into patterns of sequences and then looking into the patterns of adding up all the terms of the sequences. But really, it's more about what goes on in section 9.5 itself. When you're studying differential equations, say the circuits problem that I'm scrolling past, or this one with a couple edits thrown in, this is a wildly hard problem out of nowhere. We can solve this, but you need the fundamental theorem of calculus part 1, which is never a fun thing you want to use. That's why we always just throw it on paper every time we have to use it. It's one we're probably not as familiar with using, but it really has to be used down here. And the implied problem above, if the information was just slightly different of how all this combines, we might have had to use fundamental theorem of calculus part 1 again. But there's a better way. Sequences and series can give us a better answer. So that's kind of what we're getting into. First, what we're going to do on these notes is completely solve this problem. I missed the initial condition. So after we solved the problem, good observation in class was, don't forget the initial condition. Thanks for spotting that. So here's the solution there. And I also missed the current at time t. We found the charge. Then we found the charge that solves the initial condition, no charge at time 0. But also we want the current. And nothing in this problem actually says what the current is, I bet you if we really went back to that example 3 and 3.7, it would tell us. And this is the information. The current is denoted by I of t, and it's just the derivative of q. So all we had to do to finish off this problem, let's do it right here, is say the current is I of t, which is going to be equal to, take the derivative of this up here, constant here goes to 0. -3 is going to turn into positive 12 through the chain rule, e power -4t. So I copied e power -4t, multiplied by derivative of -4 through the chain rule. And that's all we had to do for the last bit of that problem. But you can't really do it unless you know what you're doing. So I'm glad we kind of waited on that instead of just guessing. Any last questions at all, folks, on the applied problem? Okay, next problem is more of a motivational problem. It's the motivation for why we're launching into chapter 11 is the thought here. So first, let's review this again. It's not our first time using that fundamental theorem part 1. It's always good to review. It says, in essence, if your function is continuous on AB, there's a guarantee on an antiderivative. It's a longer word than I remembered. So you can guarantee find an antiderivative of this just based off that minimal set of information. All you need is continuity on a closed domain. And the way that our author expresses that antiderivative is defining an integral function where the input x is the upper limit of integration. Lower limit a doesn't have to be that value. It can be any value in the integral. But once this is defined, we can say here, the derivative of g is equal to f of x. But that's just a way of saying it's an antiderivative. G of x equals the integral from a to x, f of t dt plus a constant c is an antiderivative. So with that information in play, we can now solve this problem here, and we'll pull in the weirdest antiderivative ever from Fundamental Theorem Calculus Part 1. Well, the reason it's antiderivative, just for another reminder, is if you differentiate that function, f of t turns into f of x, and that's the original function, the integrand itself. Only reason it's f of t here, just as a reminder, is to avoid the conflict of notation, x being also an upper limit of integration, and the variable of integration makes it a little convoluted. But now let's solve one last differential equation. I mean, it's a good review on this process as well down here. This is already in standard form because we have 1 in front of y prime. We have 2x, and this indicates that the p of x function is that. P of x equals 2x. That implies right away that the integrating factor I of x, I think we usually use blue for that, is e to the power of the integral of the p of x function, 2x. And so this turns into, let's say, sort out the color coding, e to the power x squared. So now it's kind of like a power tower of stuff. There's really an association here. It goes like that, but usually it's dropped off. So it's e to the x squared. We multiply all sides of this by e to the x squared, and now we have e to the x squared y prime plus 2x. This is the p of x function part, e to the x squared times y equals e to the x squared. So that's the multiplication through. And even here, you still want to do that check. Consider the e to the x function. Look into all of that. And eyeball it, double check that the derivative with respect to x is really this. Yeah, it's got to be. Derivative of that would be itself multiply by derivative of x squared through the chain rule, and it takes on that form. That tells us we're on the right track, so the next step is that e to the x squared y prime. Oh, I made that same mistake from before. Once again, don't make that duplicated mistake from last class. Prime goes on the outside of the parentheses, not on the inside, equals e to the x squared. And because I'm running a little bit low on space, this one time on the notes, I will take this little shortcut here. Let's just integrate it now. Integrate the left side by dx, integrate the right-hand side by dx. And I'll go first. Left-hand side is e to the x squared y. And now we need an antiderivative of the right-hand side. Here's where we hit major problems in mathematics. It's really kind of weird. The landscape of the world of functions is incredibly vast once you start thinking about integration and differentiation. Give me any function, we can differentiate it. We have the algorithm, all of the differentiation properties and tools to do that. But give me any random function and ask me to integrate it, all bets are off. If it's just right, like cosine squared times sine cubed, like in section 7.2, we can integrate those. If it's a rational function, we can use a partial fraction decomposition. But if it's something like that, we might not be in good shape at all. And these are easy to write down. Take into account something like sine x, we were talking about at the start of class, divide by x cubed. I don't think that this one is easy to solve either. We need power series methods to get an antiderivative here. We need power series methods to get an antiderivative here. And so instead, we'll hit it with the fundamental theorem of calculus part 1. And again, it's really weird what's going wrong with this one. U substitution works, integration by parts doesn't work. I said works. U substitution does not work. Everything is just wrong about this function. Unless there was an x there, then suddenly, no problem, we can handle it just fine. That's the weird thing about functions, is that integration is an unfriendly process. Whether you can actually find a closed form answer to any problem whatsoever absolutely depends on how nice the function was. So here, because as our author does mention in a couple places, this one has no elementary. It's kind of a weird word. What we mean is just an ordinary function, like say x cubed times e to the x, something you can write down with finitely many arithmetic operations. There's nothing like that. So we have to use infinitely many arithmetic operations to get that antiderivative. So we say no elementary antiderivative. Still, we want to solve the problem right here now. So with the fundamental theorem of calculus part 1, here is an antiderivative. We're going to use the integral of the function f of t. That's this function right here. The value x that we put, or the better value, a, that we put in the lower value. Well, who knows what that would be? They didn't give us a domain, right? But a natural choice would be that 0 coming from the initial condition. So we'll pick 0 for the lower limit and say antiderivative of this part, let me zoom out just a touch, is equal to an integral from 0 coming from our initial condition, go up to x. We change the actual variable of integration and go e to the t squared now, dt. And just like we indicate over here, it is an antiderivative. We need the most general one. So we add a constant c at the end. So that's the solution. Next thing we do is pull in the initial condition here. Weird way to do calculus, right? We couldn't solve the problem. So this is a guarantee that there is a solution. We just put it down on paper. Well, next step, take the initial value that y at 0 is equal to 5. And this means when t equals 0, y itself equals 5. We're going to plug that into the left-hand side over here and go e to the power of 0 times 5 equals an integral from, now here's the reason why we really want to pick 0. We're integrating from 0 to what I do here. Oh, I should have called that an X. Sorry about that. I think I got mixed up with that variable t. Somehow my brain thought the variable of the whole problem was t. Let me backtrack on one step here. Should be x equals 0. That's an x value, not a t value. And that fixes my problem because I was looking for a t to plug in. There is no t. We're plugging into the upper limit of integration, that value of 0 right here. That's the only reason we chose 0 for that lower limit. This whole thing doesn't matter what's inside of it any longer, either the t squared, dt, that whole thing is now 0. We still have the constant c, and that's our objective, solve for that there. Well, any questions at the moment? Okay, pushing through, next step we have on left-hand side, just a 5. On the right-hand side, one big 0, like the world's fanciest way to write the number 0, plus c. So 5 equals c. We'll drop that back over here and solve for the function y. So last step, we have the y equals, I'm going to divide both sides by e to the x squared, but really write it in as e power negative x squared. Multiplies all of this stuff, so go from 0 to x, e to the t squared dt, at the constant c, which we just found to be 5. And our job is done. That's the solution to this differential equation. And it's really weird again, right? The problem that we just solved, the applied problem, had a more complicated looking differential equation, but this one's harder. And change things around just right in any applied problem, and this can come up out of nowhere. People still need the solution, they still need to evaluate this, but now when you evaluate y at any value x, you plug in that x value here. Say, suppose you're doing y at 3, that'd be e negative 3 squared, integrate from 0 to 3, e to the t squared dt, plus 5, and that's the function at 3. How would you even compute that? We still don't have an antiderivative for e to the t squared. That doesn't change the fact just because we use the fundamental theorem. But now you have Simpson's rule, trapezoid rule, all those other approximation methods could be used right there. And that's what's occasionally done in differential equations. But it may not be the best way to estimate, because if we really put in an actual Taylor series or a Maclaurin series, the convergence of the series is faster than trying to do these sort of approximation methods by hand. So if we do this all just right, we get a better answer with even faster convergence to the true value of that integral right there. So that's the whole reason of chapter 11. Even in this applied setting of section 9.5, really abstract things come up out of nowhere, and we want a way to wiggle out of that and put something better in for the answer than this right here. But this is where the problem ends. This is kind of a side problem, so this won't come up on homework or exams. It's just a problem to be good, to be aware of. These things come up all the time. Well, we did it, folks. We're done with chapter 9. That means we've completed both of our application chapters, chapter 8 and chapter 9. Chapter 11 will still take some time to find some applications when we get to them, but really, this is the application. We'll redo some of these kinds of problems, actually integrate e to the x squared, so that we can provide some better answers. So we'll look into this differential equation again once we get towards the end of chapter 11. Let me save this up, and now let's start up that chapter 11. What was the reminder though? Oh, to determine current. Okay, we hit that reminder. Taking its time to close. Let's give it a little bit of a break. There we go. Well, this is not the last chapter of the course, but usually in Calculus 2, it kind of feels like it. We're doing it right now because if we did chapter 10 now, it's easy to put ourselves in the uncomfortable situation where we're doing the most abstract part of the course on this week here, right after exam 3. And that's just not a good opportunity to actually learn this kind of stuff. So we'll do chapter 10 around these weeks here. After exam 3, we'll just do a couple additional topics. And chapter 10 connects better to Calculus 3 in the first place, making that pretty decent approach. Well, chapter 11 starts off with sequences. Think of sequences as being a function that's no longer continuous. Let's say it a different way. Abstractly, a sequence is a function f that maps the natural numbers, think 1, 2, 3, and so on, depending on how you define the natural numbers, to the set of real numbers. So here what I'm saying is f is the function, the domain is 1, 2, 3, 4, 5, the ordinary natural counting numbers. The range is any real number whatsoever. So that's what we mean by a sequence. It's as if we're taking a function that ordinarily looks like this, but we're making it discrete and just putting in what the function outputs would be for integer values. No longer a differentiable function in any sense of the word differentiability. But the weird thing about all of this is the sequence is where your function is just scattered, disconnected, isolated dots on the graph. But when we get to the series, it's as if we're connecting the dots. We're defining a new function, summing together all the terms of the sequence, and now we have something that is differentiable. So the series and the power series are things we can differentiate and integrate. So this is a really mysterious chapter. We're starting with something that is disconnected points, adding the values of the terms together, and it connects them to something that is differentiable. Example 1 here is kind of a redo what we did on the last notes. Honestly, I forgot I left this on there. The motivation for the problem in chapter 11, the last problem we just did, was supposed to take place of this one. Let's integrate it just for the sake of it's here. It'd be weird to skip it in the notes. Antiderivative of this would be integrate from whatever value seems convenient.
Wait,
Sorry, say
the
again.
Doge Anxiety song? I thought you were saying.
I think that's open mic, but let's say any value that's convenient would work here. You could go 5, that'd be appropriate. I would just go 0 without any further information on what I should put down for the lower limit a. Either the x squared didn't come in with a finite domain, but we could say take a domain that starts at 0, go forward, or any real number that's convenient. We go up to x, put in either the t squared, dt, add a constant c, and again, sorry, that's just a review of what we did before, but second look at it. That's using the fundamental theorem of calculus to find an integral, to integrate this. It's a dissatisfying answer in a lot of levels. And so just reiterating our goal, chapter 11 is going to find us a better way to solve this. So this first example is just a redo of why we're here. Should have deleted that, but forgot. This is where the notes really start in earnest finally. So sequence is a list of numbers written with a definite order. The order comes from the fact that it's truly just a function, f, mapping the natural numbers to the set of the real numbers. How does that mapping work? The subscript here, a1, a2, a3, comes from the natural numbers themselves, and whatever their values are could be anything. It could be pi, square root of 2, 0, 1, 12 here maybe. So the output is in the real number system. And this is how we write the function notation now that we're in the land of sequences. This is really pretty weird. In function notation, you would say a1 is f mapping the integer 1 to some real number. This is how we would ordinarily say it if we have a function with domain the integers and codomain the real numbers. But to make it a little bit more compact in the notation, we suppress the function notation and we just say a1 itself. So a1 is f mapped to integer 1, a2 is f of 2, and so on down the line. There is no f of 0.5. F of 0.5 is automatically undefined. 0.5 wasn't special. This is just saying anything that's non-integer, well, anything that's not a positive integer is a better way to say it, is automatically undefined. Those 1, 2, 3, 4, and so on is the domain of the function. Then other notations are, when we're dealing with a sequence, the definite order has to do with the ordering of the natural numbers. And we call A1 the first term, A2 the second term. And we'll often say AN is the generic nth term. A lot of our methods are going to be about the nth term when we're determining convergence or divergence. And by the way, we do carry over that information from section 7.8. All of our conclusions in chapter 11 are essentially going to be something converges or something diverges. So next line says, we deal exclusively with infinite sequences. That's a good reminder. So no finite sequences whatsoever. That's why there's a ... even after AN, just to say, and so on, forever and all time. This is an okay notation. A lot of sequences are written out this way. Sometimes we drop the parentheses or the curly braces and just write out the sequence. No, it looks like I kept it on there. If we drop the curly braces, we could still say we're dealing with a sequence. But if we want to really convey it's a sequence with infinitely many terms, this notation is pretty handy as well. It's kind of like summation notation. When you're adding up a bunch of integers, you write down a notation that goes summation from n equals 1 off to infinity, nth term of, say, the sequence. This would be the series that we're looking into the next time. And this notation is just kind of trying to inherit that format. It's saying, you're really dealing with this. The nth term is an. You start at 1. It's infinite, so you go off to infinity. So already this is kind of convoluted, right? That's why we're spending some time here. You can indicate your sequence like this. List out the terms. You can indicate it this way, specifically saying where it starts, that where it ends or does not end if it's infinite. Or you could say it this way. If it's already implied that you start at 1 and that's an infinite sequence, you can drop the sub and superscript and just say an. And the last way is sometimes we just say an itself and call it good. That's what's being written down here on our first example. We say it's a sequence and we just indicate its nth term is 1 over n. But again, there's loads of different ways to write that out. It says to write out the first 5 terms. That's these right here. Oh, that's not those terms. That's the using the domain 1, 2, 3, 4, 5. And plotting them. Kind of a tedious task, but let's give it a try. Only reason we want to plot the sequence is just to get a good view in our mind's eye of what are we really dealing with the moment we write down something like that. The moment we put something like that on paper or something like that on paper, we need to have a picture in our mind to really help us out with what's going on. It's not because section 11.1 is hard. I think a lot of people enjoy this. It's kind of a redo of Calculus 1 and limit methods. What's hard about this is when we go from a sequence to a series, it becomes really convoluted out of nowhere. So we're spending some extra time right here to really reinforce, get it down in our mind, pat, what is a sequence? Best way to do that is just plot it. So let's give our by hand plot of the situation. First, consider the domain. We're using the ordinary integers. So that means we'd only be using quadrants 1 and 4. And it's no longer an x-axis. This is an integer n-axis. Kind of weird already. We start at integer 1, so we're not even plotting on the origin. We're starting right here. So the plot moves to the right, not at the origin, like a normal function. Since we're plotting on this domain, we'll go 1, 2, 3, 4, and 5. There's infinitely many terms, but we should be able to find the limiting value of the sequence just by considering the first 5 terms. And this is the function, a of n equals 1 over n. All we do is plug in 1, a1, use this form, you'll get 1 over 1 for a 1, and then just plot it out here. There's the first term. Not so bad, right? All we're doing is taking this, plotting discrete points. We go off to the next domain element, 2, call it A2 for the scratch work on the right. Use the format of the nth term of the sequence, that's 1 over 2. I'll call it 0.5, and we're on our way. Next value would be here. I should set the scale on the axis. So here's 1, here's 0.5. That's the next term. And you've probably already seen the pattern, right? At each successive term, you, well, divide it by 2, well, not divide it by 2, you divide by the term itself. Next one is a third, next one is a fourth, next one is a fifth. Let's just write that out though. We get a third, so 0.3 bar. And this is where it's getting a little bit hard to plot. I'm going to say, looks like about a third right there. I'm just eyeballing it. A 4 is 1/4 for 0.25. And a quarter, that's not so bad. Let's go halfway. About right here. A fifth is 1/5 for a 0.2. Getting a little harder again, maybe about there. You have to resist the urge from your training in algebra to connect the dots. The sequence itself is the disconnected graph. There's infinitely many more terms, and I can't go ... to convey it. That's a miscommunication. But from the view of just looking at the first 5 terms, what would you all say the limiting value is for the sequence? I agree. From class, folks said 0. Anyone have a different take? Well, I totally agree. The way we would say this, though, is what is the limiting value? We take lim for the limit. And another urge we have to resist is we don't say x going to infinity. X has nothing to do with this problem. It's always n now. The limit as the integer n goes off to infinity for the nth term of the sequence, that's an, turns into the limit as n goes to infinity of 1/n. And from our training in calculus, we know that if something is finite in the numerator, but the denominator is allowed to grow without bound, limit is 0. Or another way to think about this is, that's a rational function. If you're taking it off to infinity, the output is automatically its horizontal asymptote, if it has one. So every time we take a limit of a sequence, that's what we're providing, the horizontal asymptote, if it exists. Because that's the direct connection with that limit right there. Well, it's weird as well. Think back what the oddities here are in calculus, because an is 1/n. It's non-zero for all n in the natural number system. So for every integer n you pick, you never get 0. Yet down here, we say the limiting value is 0. What this says is, well, we don't pick up 0, but we can get as close to 0 as we'd like by taking n to be sufficiently large. That's all we mean by the limiting value. It's the value that we keep on approaching, getting closer and closer to, as n itself gets larger and larger. It looks like the points get closer and closer to 0, so we made that convincing argument. Well, any questions at all, folks, with that statement so far? Okay, so this is here the sequence. So what's the series? We're not even in that section, but we always have to keep the two concepts separate in our mind. This is a good time to do it. The sequence looks like this. It's just discrete points, and you're wondering what happens to those points as n gets large. That's the whole concept with the sequence. But the series is different. The series is where we go a1 plus a2 plus a3 plus ... And that ... goes on forever, nonstop, add up all terms. Well, how do you do that? We are finite people. Our computers are finite devices. You cannot actually add together infinitely many terms, but you can do this. You can take a limiting value as n goes to infinity of the summation. Let's say, you know what, I think I need a new subscript here. Let's make it be k goes off to infinity. N goes from 1 to k of an. So what this is saying is add up k many terms, see what that number is, then increase k by a little bit. If that term, next term, when you add the next value, it gets larger, so much that in the limit, it keeps growing and growing and growing, we'll say it diverges. So over here, a limit of 0 with a finite number means converges. And now on this one down below, these converge sometimes too. But one really gigantic surprising fact is that this one diverges, which is massively counterintuitive because the terms are going to 0 in the limit. But they're not going to 0 fast enough. If we attempt to add up all the terms, we have divergence here. If it was 1 over n squared, we have convergence here again, even faster. And we have convergence when you add up all the terms, the series itself. Really bizarre in a certain sense. In fact, 1 over n to that 1 power is the division case where the series diverges or converges. The power is anything bigger than 1, automatic convergence here, and at 1 and lower, automatic divergence. That means this series, it can be re-expressed as summation n goes from 1 to infinity of 1 over n coming from the an, which is 1 over n. You know, I should probably connect that thought. Limit k goes to infinity, n goes from 1 to k, summation. I just want to say that an is the 1 over n for comparison's sake, and this diverges. It turns out it's a really useful example for us. This is the division case between convergence and divergence of the series. And because it's so critical and fundamental, we call this one the harmonic series. That's kind of an interesting name. I've never actually dug into why it's called the harmonic series. There's got to be a pretty good reason for that. So that's a side project if anyone wants to look into that. It's from the music, just looking at tones.
You deal with like, dudes or whatever that actually makes music.
Oh, I see, yeah.
They have to be like perfect or they won't,
Same like on a guitar then too, right?
Yeah.
Interesting. Thanks for that. I never actually knew what that was referring to. That comes from music. That's a great comment to throw in there.
I think that's why I was thinking from music.
That seems really absolutely believable the moment you said that. I don't know why I never connected that thought, but this comes from music. That's really awesome. So harmonic series, it's really weird. We're going to see, well, our author is going to prove the divergence of this. We're going to prove it through the integral test, considering the right and proper integral. But for the moment, we should do this all over again. Here's our example 2 right down below. I think I have a typo here. It says right out the first 5 terms. This should say 20 terms. Let's start off by just fixing the weird mismatch in instructions. So we have an being 1 plus 10n divided by 9 power of n. We want to plot the sequence on the domain using technology. So I can't ask this question as a real homework question. Think of this as more of just a classroom demonstration. And then we'll come up with the limiting value of the sequence. So fastest way to do this is just to use Excel, I'd say. Maybe not be the cleanest way ever, but if we want to do it just right away without too much coding going on, this would be a great way to start. So first thing we want to do is throw in whatever an is. Let me start off differently. Begin with a domain element, n, then go to the actual function value, a sub n. Next thing we're going to need here is the domain elements, 20 terms. Let's organize it this way. So go 1 here to get it started. Go equals this one, plus 1 to get the next ones going. And let me, oh geez, let me extend this down a little bit better. Should be able to drag that down. I think I need to go a little bit further. And there's our 20 terms. So that's the domain element on the left. Now on the right, we put in the function. It's equal to 1 plus. Then we can fix the formatting there. You could just say 10 divided by 9 to power n. Makes it easier to type in. 10 over 9 power n. Oh, and we shouldn't say power n, right? What's the better fix on this, would you say? How about a2? A2 is the right power, so we have the power we want to put on the left, the function on the right with their specified power. Okay, so it says if you plug in 1, you get something slightly larger than 2. That looks right. If the denominator was 10, it would be exactly 2. And now this carries down. If it's at 2, we get 2.23, because now on this line, observing the function, it's using 1 plus 10 divided by 9 to the power a3, but now it's just to power 2. So this keeps on conveying down in this kind of way. And here's the first 20 terms. Looking at all that, what would you folks say about this so far? We need to plot it, but just looking at the raw data, I agree. That doesn't look like convergence at all. It starts small and it grows. But you know, if it slows down in its growth rate, it would have been convergence. It doesn't look like that. It looks like, if anything, it might be accelerating in its growth rate. We view it in a slightly different way. Let's take those two columns. I think data is where we want to go. And, oh, geez.
I think it's
Insert, thank you. Insert, and there should be a decent one. There's the plot of our sequence. That's definitely a picture of convergence. Look at the concavity of this. It's concave up, which means it's growing faster as you move to the right. Well, that's got to be the case, right? If we had both of them converging, that wouldn't be two good examples. So here's our divergence example. And you know, even though it's kind of just a quick demonstration doing 20 terms, so we don't have to do this so tediously, this is kind of a valuable tool as well. If you're just not sure what's going on with your sequence, you can plot it to get some extra intuition of what should happen. We still have to show the steps taking the limit and all that fun stuff, but that's going to be later on in these notes. All we want to determine is, what is the limiting value of the sequence? Qualitatively, based on what we see, we can say limit n goes to infinity of an, which is now limit n goes to infinity of that 1 plus 10 n divided by 9 power of n, kind of a weird format. Well, this is diverging, so we'll just say is infinity, and that calls it good right there. Our overall statement for our conclusion then is diverges. Might be a good idea to say what diverges. It's the sequence an that diverges. So that's the view of what a divergent sequence looks like. And we did by hand what looks like a convergent sequence. But later on these notes, what we really want to do is apply all of our limit laws, same ones from Calculus 1 with just some adjustments, to actually doing these in a better way. That way we don't have to guess if it's convergence, because maybe 20 terms wasn't enough. Maybe not for this function, but something more complicated. Something happens after a certain point and it really turns around, the inflection changes and it could level off. Using a finite many terms informs us, but it's just numerical evidence. It's not the end-all answer. In fact, if we do make a change on this, we can force a convergence. Here's the change. The only reason this diverged is the thing being raised to a power, it's bigger than 1. Go 9 over 10. Carry that all down. This is the picture for converging. It's not clear that it's exactly converging, but it looks like it's plausible. It probably converges to 1 exactly. And that would be because 9 divided by 10 to a power n just gets smaller and smaller, goes to 0 in the limit, leaving just behind 1 itself. So make an adjustment, and now you have convergence. And that's part of the name of the game with all of our tools in this section. We look at the format of the function, determine what theorem we have to use from the limit laws in Calculus 1, execute the limit laws in a better way than we did right here, and get our conclusion. So that's going to be the flow for pretty much all the problems in this section, except for the next one. The next one's kind of an odd one out. But any questions at the moment? Okay, here's the one that's the odd one out. It's an uncomfortable problem. Nobody likes this problem when they see it the first time. And it's kind of a concerning problem because we're not doing it for the novelty of it. This is something that we have to know how to do all over chapter 11. In particular, at the very end, we do this a lot. When we derive our Taylor series and Maclaurin series, this kind of work comes up. We want a formula for the general nth term of the sequence. Only finitely many terms have been provided. But first, let me be honest about this kind of problem. There's something totally unwritten here, and that is, if finitely many terms are given, there's in fact infinitely many different ways you could complete a pattern, including just that information. There's more than one right answer to this, in other words. But when we do a problem like this and it says find a formula, we're thinking about the most obvious pattern, the one that just fits this, doesn't do anything crazy after the next terms, the next 5 terms. So when it says find a formula, think of, for example, when we wrote out, oh geez, too far, 1.5, 0.3 bar, 0.25, 0.2, we were thinking specifically this one, even though we could potentially come up with another sequence that matches that and then changes after the 5th term. So after that honesty about the problem, here's the next honest thing about it. It's a trial and error process. That's the uncomfortable thing about it. But we get better at this as we go. So on the left, this is going to be the trial. On the right, we'll evaluate what we have. If we make an error, we'll redo the trial. First, we look into the elements we see inside of this. We see powers of 4. And so even though this may not be right, not a bad idea to just start off. Let's put a power of 4. It's trial and error. We'll make a correction here as needed. Other issues are, if beginning positive, flips to negative, back to positive, negative, positive, and so on. So it's a special sequence. This is an alternating sequence. And when things are alternating, the automatic thing you want to do is go -1 to a power. And like before, I don't know if that's the right power yet. We'll do our trials over here. Well, this is the trial, and we'll see what we get. First, A1, if we plug in 1 here, we'll get a 4. That's encouraging, right? Doesn't mean we have the right pattern, though, because this has to work for all terms. It just seems like it's in good shape. Plug 1 here, and we get -1. Already, we found a problem. At A1, we begin with negative. We have to begin with positive. Anyone see what the fix is here on purple? Here's one thought. We have to be at +4, but we got a negative. Just go like that. It's positive now, right? But that means you multiplied by 1 extra base of -1, and that should fix it. Go n+1, and we're all set. Again, it's weird math, right? It's kind of like factoring with trial and error. You put things in the right spot, see if you FOIL just right and get the middle term to come out right. Sort of like what we're doing here. This is still not the answer, but this is a process. So if we don't show what the process looks like in trial and error, there's no real support in the homework. So we made an adjustment. We start over and do A1. A1 is going to be 4 times 1 here is -1 squared, so it's a +1 as required. And again, never celebrate early. That just because we got the first term doesn't mean we have the pattern right. That's the earlier comment we were making here, is that even with 5 terms, lots of ways to make this pattern work out. We're just going for the most obvious, easy to get pattern. Let's go to A2 and see if it's satisfied. At A2, you have 4 squared, so 16, times -1 to the 3rd power, odd, so -1 now. We get the negative, but we are way off on the power 16. This calls for an adjustment on the power n. Anyone see what the fix could be?
You make the 90.
Yeah, it looks like that's what's going on. And good call on that as well with this information. If we have powers of 4 emerging in the denominator, then really our big fix should be 4 power of n shouldn't be there. We should go a sub n equals 4 power n like that. Power's still not right, so we need to make an adjustment here. If we plugged in 1, let's back off. We would get, let's see, the positive in the numerator, but we get 4 in the denominator. We need to flip that around. We want here a power of -1, right? Because then it would be 4 power positive 1, the thing we're really trying to hit. So what could you put in here so that when there's a 1, you get a -1? Anyone see the fix on the exponent in this location? Close, but the trouble with -n is if we put in a value here, oh, hang on. You know what? I think that works. Let me take a look. We plug in -n at 1, we're going to get -1 squared, so positive 1 in the numerator. 1 down here is 4 power -1. Oh, that's the wrong pencil. And we get 4, but never celebrate early, right? That's the mantra with these. Go to A2. At A2, odd on the exponent up here, so -1. And 2 here is going to get us 4 power -2. And out of nowhere, this is kind of soul crushing, right? Mismatch on the pattern. We don't have that at all. We have -16 altogether. One more adjustment and we can get there. If it's a -1, that means what should have really happened here is it should be 4 to the power of 0. That's what's going to make it right. If it's 4 power 0 when a is 2, what has to go here to make a power of 0 when n is 2 in that location? And you can see what we need to throw in this spot. Let's see here. Let me throw in n minus 2.
Couldn't you keep the -1 n plus 1 for n and then multiply the entire thing by 16?
Take, let's see here, a -1 over,
Like what we had originally, the original sequence we came up with, right?
what did it look like? Sorry, I totally forgot.
Yeah, the -1, then the n raised to the power of n over 4n.
Gotcha. Well, trouble with this one is the moment you go
and
to,
multiply by 16, what is that? Give you-
oh, I got you now, multiply by 16. I like that approach. Multiplying by 16 is going to give us a power of 4 essentially. So this would then become -1 power of n, 4 power of n times 4 squared. And this does directly give us our fix. It should have been n minus 2, it looks like. Let's take a look. This then becomes -1 power of n, 4 to the power, take n minus the power 2. And I think we're in business on this one. Let's double check though. Plug in 1. Oh, I think we still need to add a power here. Now plug in 1. Back over here on our check, we're going to get positive 4 power -1, which turns into a 4. That's exactly what we're looking for. Now at A2, plugging in a 2 is going to give us odd here by the red dot, so negative. 2 in the denominator is 4 power 0, but that's exactly what we wanted, right? A 0th power gives us -1 altogether. Our problem term is now resolved. Still, it's always a good idea to keep on going. It's easy to get the 2 terms to match up, but a problem in the 3rd term. I don't think it'll happen this time, though. I think we're really on the right shape with this. At power 3, even for this exponent, so it's 1. And in the denominator, it's 4 to the power of 3 minus 2, so power 1, matches that term. At this point, I'm pretty convinced, but let's write this out just to be extra sure. Odd with n being 4, so -1 in the numerator. So it'd be 4 minus 2, so power 4 squared. That gives us the 16. And you know, at this point, I probably would give up and say, I'm pretty sure we've got it. because at power 5, that would be even. So let me say again, even so positive, this would be 4 cubed, and 4 cubed is 64. So we've matched it up. Not the most funnest process in the world, but we did it, folks. AN equals that is the generic nth term of this sequence, where again, we're making a big assumption, even though we didn't say it. We're just looking for the most obvious fat pattern that fits this all together. And that would be this one here. Kind of uncomfortable. We're going to redo this kind of process in section 11.2 and just scattered throughout chapter 11 so we don't get rusty in it. Because it comes back in a huge way, like we mentioned, once we're in the Power series, Taylor series, Maclaurin series. And when these problems come up, if you get stuck on them, if you need some hints, don't hesitate to reach out. This is just meant to be something we're trying to pick up early as a skill. And it's easy to just find that you're not sure what to try. Don't hesitate to reach out for hints. Well, let's see, we've still got 12 minutes. Next concept we're going to do after introducing sequences, dealing with all these concepts of plotting, coming up with generic terms. Next thing we're getting into is the fun bit, limit laws for sequences. And all of these limit laws, you could compare back in Calculus 1, no different than saying limit x goes to infinity, f of x plus g of x equals lim x goes to infinity, f of x plus limit x goes to infinity of g of x. So that's our first limit law from Calculus 1. But if we change the function so its domain is integers, we say the limit as n goes to infinity. We don't use function notation. An is really f at n. Right-hand side is the function notation. This is the way we write it in for sequences. That was always a weird mental kind of break there. But after getting through those two things, this is saying the same exact information. The limit of the sum is the sum of the limits. Limit of a difference is the difference of limits. Constant multiples can commute outside the limit operator. Limit of a sequence that's always a constant is that constant. That one's kind of a fun one in a certain sense. It would say, if your sequence goes 1, 1, 1, 1, put in a dot, 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 because it has to be an infinite sequence, equals an, then by that rule we're looking at, the limit law 4, all we would say is limit as n goes to infinity of an, it's a constant function, it's literally just 1, is 1 itself. But it's kind of a weird property because here you're viewing the actual 1 plugged in, but it's really talking about the sequence. So you want this in the back of your mind as well. Just a list of dots constantly at height 1. The limit of that is just the constant itself. This is a nice rule that breaks down if we were differentiating. Another nice rule, and this rule works out great as long as your power is positive and an is positive as well. Let me take another look at that. Okay, so that's the last limit law. I was getting a little mixed up on the requirement of a positive power on this one. I think what we're trying to eliminate is the power being, say, something like a negative 1/3 could be problematic if this converges to 0, because it's going to drop it to the denominator. I think mainly what we're trying to exclude is not so much by the power, but if the power comes out as a 1/2, then we don't want an to have negative terms. We want an to have positive terms. Otherwise, we're taking square roots of negative values, and we're in complex analysis at that point. So just to keep everything a real number, that's what these conditions are right here. So we inherit all these from Calculus 1. And down below, all we're doing with the next examples is taking some limits, considering a new theorem each time we go. So let me just show you the progression in the notes. Theorem 4, it'll be a new property. Theorem 6, a new property. And then finally at the very end, we'll just do some random problems where we do all the properties at once. So let's make this one our last one for the day then. We'll come back on Thursday's class and move through the rest of these limits. Theorem 3 is massive, and it's one of those theorems where we talk about it once, we make a big deal out of it, and then we just take it for granted for the rest of the course in chapter 11. Essentially what it is saying is, if you take the information from calculus 1 on doing an ordinary limit with a function f of x, and if the limit comes out as L, then even if you go down to the land of sequences, so this is now a sequence, in the land of sequences, you can take the same limit, but change to n because n is an integer, and whatever that limit came out as, it will be the same. So theorem 3 is essentially now telling us everything that you did with the continuous function in calculus 1 can be re-expressed with a sequence, giving you the same exact limit. That's a powerful statement. Another view on it is we take this as a temporary screenshot. And I went too far. Let me put it back over here. So just another view temporarily of what this theorem is trying to say is we're trying to take a limit of an, that'd be the limit of the discrete points. However, allow yourself to connect the dots, even though we said not to, for the sake of just doing the ordinary limit. If you do limit as x goes to infinity of 1 over x, ordinary theorem from calculus tells us for constant in the numerator, and x is to a power higher than 1 in the denominator, greater than 0, then it's automatically 0 itself. Same conclusion we got. But then we could just say it immediately and automatically. Therefore, limit as n goes to infinity of 1 over n, also 0. So this is the content of what theorem 3 is really trying to say. Any questions so far about that theorem? Okay, here's how we're actually going to use the theorem on this example 4. Notice that example 4 is tricky in a way. If you want to take the limit as n goes to infinity of n e power of n divided by n squared plus 1, first thing you might observe is that this is an indeterminate form because n e to the n goes to infinity and n squared plus 1 goes to infinity as the integer n goes to infinity. So we have indeterminate of type infinity over infinity. And that's okay because L'Hopital's rule is designed to correct that, right? Next problem though is, if I use L'Hopital's rule right there, would it even make sense? Because if you use L'Hopital's rule, your function is the sequence now, and the sequence is discrete points. There's no differentiability here whatsoever. You can't differentiate that function. However, take a different view of this. The different view says, if you train a function so that its definition is exactly the same, just switch the domain from the integers to all real numbers, now it's continuous. All you're doing there is connecting the dots so you can take an actual honest derivative. Let's do just that. Then we'll mention the shortcut at the end on this. We'll say here, define f. It's now going from R, not from the integers now. We're doing a real actual function. I shouldn't say a real function. We're doing a function with domain, the actual real numbers is the better way to say that. We'll define it as f of x equals x e to the x divided by x squared plus 1. And we can totally take the limit of that function. We'll find the limit L. We'll use L'Hopital's rule, and there's no logical worry about that. Numerator and denominator are differentiable. But once we get the limit L, we'll come back to this one and say, oh, it's the same limit over here. So here's what our next steps are going to look like. By L'Hopital's rule, we can say limit as n goes to infinity of f of x. That was weird to put that there. Hitting it with L'Hopital's rule because it's the same indeterminate form, infinity over infinity. And we get limit n goes to infinity. First is the product rule, take the derivative of x. So it's 1 times e to the x plus derivative of e to the x. So we get x times e to the x. That's kind of a wild fraction bar. Let's fix that. Then in the denominator, we get a 2x. And observe with this format, still a L'Hopital's rule problem, right? Numerator grows without bound to infinity. So does the denominator, just not as fast. So we use L'Hopital's rule again. Limit n goes to infinity. Over here, derivative of e to the x is itself. Over here, when we go to differentiate that, it was the same as differentiating this. And the result was that. So we don't have to redo the product rule. Let's just grab the result that we already provided when we did the product rule. It's e to the x plus x e to the x. And now our denominator on all of this is 2. At this point, it is determinate. We lost the indeterminate form, infinity over infinity. Numerator is going to grow without bound exceedingly rapidly. It's a combination of exponential functions. Denominator is finite. So that means the whole thing is infinity as an output. Well, if that's the case, we can conclude through theorem 3. Therefore, limit as n goes to infinity, n e to the n squared plus 1. One little logical thing that's being not well conveyed here by this theorem is that when it says L, they mean an actual finite number, not an infinity. This is a does not exist as a limit, but it's also a particular way it doesn't exist, blue up to infinity. This theorem still applies if we get an output of infinity. The theorem can be extended to infinity here as well at the same time. Just isn't really well conveyed with the way it was written. But even if it's an infinity, back over here, same exact output, infinity as well. So that's the use of theorem 3. But I have one additional comment. The big overall statement about theorem 3 is that theorem 3 enables, if you choose to do so, it still will look weird on paper, but it's an acceptable shorthand. It enables us to use L'Hopital's rule on limit n to infinity, n times e power of n squared plus 1. So all the steps we would have taken using L'Hopital's rule, even though we know we can't differentiate it, would look exactly like all of this. Just swap x for n. Because of that, if you did use L'Hopital's rule and you left it as n's, sure, that's a huge abuse of notation. But my assumption, and essentially everyone else's assumption, is you've used theorem 3, you're thinking of it now as a continuous function, and that's what theorem 3 allows. So this is a decent shortcut. We'll use it ourselves in the notes and come back here just to re-explain why we're suddenly differentiating something that can't be differentiated. That's always weird. But those are comments we'll get into next class, it looks like. Sorry, it looks like this one went a minute over. But any last questions at all, folks, on finalizing this? Okay, well, this is sequences at the moment. 11.1 goes pretty nice. We're just reviewing calculus 1 limits in a certain sense. But have a great night, folks. We'll finish this off next week, move into section 11.2 as well, or next class, sorry.
I didn't know you did this morning.
Thank you, sir.
What? I didn't know you did this morning about it.
Yeah, that's right. Math and stats. Yeah, I got a master's in math did a little bit of graduate work and then decided absolutely research is not for me and got out of it quick. And a bachelor's in stats. Bowen did a lot more graduate work than me. I think he went to a pretty aggressive research program in university. He's got a pretty tremendous background, actually.
And it's like, hold on, you guys don't know that.
Yeah, yeah. Yeah, he's got a lot of depth of his mathematical background, way more than me. So he's a great guy to talk about if you're interested in graduate school, what you're getting into.
I don't know.
I hear you.